So here's a pretty wild question for you. What happens when you build an artificial intelligence that can see and understand the world, and then you try to get it to simulate a psychedelic experience? Let's dive into one of the most fascinating AI experiments I've seen in a long time.
See, the whole thing kicks off with this incredibly ambitious goal. This isn't just about taking an image and running it through some funky filter. No, the real challenge is to see if you can alter the AI's conceptual understanding of an image, kind of like what happens inside our own heads.
And this right here is the absolute key to the whole thing. When you and I see a cat, our brain isn't just storing pixels, it's encoding the idea of a cat. So if our perception gets altered, that idea gets twisted in really interesting ways. But a standard AI, it just sees a grid of pixels. You mess with that, you just get static. So the first giant hurdle is to build an AI that actually thinks a bit more like we do. All right, so phase one. Before you can alter perception, you have to build perception. The goal was to create a foundational AI, basically an artificial visual cortex that could process images in a much more human-like way.
The basic blueprint for this is a classic setup called an autoencoder. It's actually pretty simple in concept. The first part, the encoder, looks at a picture and basically writes a super condensed summary of it as a list of numbers. That list of numbers is called the latent space. Then, the second part, the decoder, reads that summary and tries to perfectly redraw the original image. That latent space, that's our AI's mental image.
But you hit a snag almost immediately. A simple autoencoder is just going to learn to compress pixels. It might see two pictures that are both very blue and group them together, even if one is a whale and the other's a car. That's useless for us. We needed to group things by what they are.
And this is where a little bit of magic from OpenAI comes in, called Clip. Clip is just brilliant at this. It can look at a photo of a cactus and generate a string of numbers that is almost identical to the numbers it generates for the actual typed-out word cactus. By using Clip as a guide, the autoencoder learned to organize its mental map based on concepts, not just superficial stuff like color. Okay, fantastic. Problem one, sorted. But solving that problem immediately slams you face first into a giant brick wall. See, training a model like this on big, high-res images would require billions of parameters. We're talking supercomputer territory, way beyond what you can do on a home setup. The solution here was just so clever. Instead of trying to reinvent the wheel, the project basically piggybacked on the amazing open-source model Stable Diffusion XL. SDXL already has a super powerful encoder that can shrink a huge 1080p image down to a tiny, manageable 128 by 128 version. So the custom AI was trained on that smaller version, not the giant original. This move took the problem from like 4 billion parameters down to just tens of millions. Just a brilliant piece of engineering. So, with this clever design in hand, it was time to start training. But let me tell you, this is where the real drama begins. This was not a straight shot to success. It was a journey of hitting one roadblock after another. Okay, so here's the first major test of your model. If it understands concepts, you should be able to blend them, right? You take the mental image of a man on a cliff, the mental image of a microphone, meet in the middle, and you should get a man on a cliff holding a microphone. Simple. Well, this is what they got, a completely garbled, noisy disaster. I mean, what on earth is going on here? The AI could redraw a single image perfectly fine, but it had no idea what to do with the space between concepts. What was happening inside its digital mind? It turns out the AI had actually learned its job a little too well. It created these perfect little isolated islands of data in its mind. You had an island for animals over here, an island for buildings over there, but the space between the islands, it was just a meaningless void. Trying to pick a point between two islands was like pointing to an empty spot on the map. There was just nothing there. The fix for this is a really cool technique called a variational autoencoder, or VAE. You can think of it as a special kind of gravity that, during training, squishes all those separate data islands together. It forces them to merge into one big continuous landscape. That way, no matter where you point, it corresponds to something meaningful. Problem solved, right? We're good to go? Not quite. You fix one thing, another one pops up. The next test showed another really deep flaw. When they tried to distort the image, this bizarre repeating 32 by 32 pixel pattern appeared. It was a dead giveaway that the AI was only seeing the world in tiny little patches, not the big picture. The solution to this is one of the most important ideas in all of modern AI. It's called attention.
By adding attention layers, you force the network to look at the relationships between every part of the image at the same time. It learns to see the whole picture, how the tree relates to the sky and how the sky relates to the mountains, instead of just staring at little isolated squares.
So now we've got to have it, right? We've got the VAE connecting the dots, and the attention layers seeing the big picture. This should be perfect. And unbelievably, the result was even worse than before. The images became this hopelessly blurry mess. It's like every single fix, designed to help it understand concepts better, was making it worse at the basic job of just drawing a sharp picture.
Honestly, at this point, you'd be forgiven for just wanting to give up. But there was one last trick up the sleeve, one final breakthrough that would finally tie all of these pieces together and fix the blurriness for good.
And the solution is a generative adversarial network. Again, the idea is brilliant. You introduce a second AI, called a discriminator, and its only job is to be a harsh art critic. It looks at an image and has to guess if it's a real photo or a blurry fake from our AI. So now our main network has a new goal, not just to recreate the image, but to do it so well that it can fool the critic. It's this constant competition that forces it to make incredibly sharp, realistic images.
And wouldn't you know it, it worked. After all that trial and error, the creator, Gal Lahat, looked at the output from this final, monstrously complex model, and his reaction says it all. The AI could finally see. The transitions were smooth, organic, and crystal clear.
So, with the brain-like visual system finally working after months of effort, it was time for the main event. It was time to actually alter its perception and see what happened.
And the method that worked best was surprisingly subtle. It wasn't about breaking the AI or anything drastic. It was just about gently nudging its mental image. By injecting a tiny little bit of random noise into that latent space, the AI's concept of what it was seeing would just constantly drift and wander around the original idea.
But of course, the million-dollar question remains, did any of this actually look like a real psychedelic experience? To find out, the creators showed the results to friends who had first-hand experience and asked them point-blank to rate how authentic it was.
And the average score they gave it was a 7.6 out of 10. I mean, just think about that. For a project built from the ground up on a home computer, that is a stunningly high score. It really suggests that this simulation captured something genuinely authentic about the experience.
So, what did it get right and what did it miss? Well, the feedback was really specific. People said the gentle drifting motion, where things seem to be moving without you really noticing the move, that was spot on. Same with the subtle pulsating of colors. But what it missed was the really organized, geometric, and repeating patterns that are often a huge part of the human experience. And this shows both the incredible success and the really intriguing limits of the project. It managed to simulate a kind of conceptual drift, but not the structured hallucinations our own brains cook up. It really leaves you wondering, what's that final piece of the puzzle that's missing from this artificial mind to make it perceive the world and its distortions exactly like we do?